This is the Pearson Edexcel FP1 paper from 2020 based on this book here. We may as well go ahead and get straight into it. First we've got to do Hospital's rule. So first we've got to just show that if we call this on the top here f of x and this g of x maybe, just show that both of those functions, when you plug in this number here, either both go to 0 or both go to plus or minus infinity. It doesn't really matter which. But when you plug this number into here, sine of pi over 2 is 1, so this is just e. This is cos 3 pi over 2 is 0, so that just goes away. E minus 0 minus e is 0, so that's fine. We're hoping for this to be 0 then. And of course, tan of, well, this should be 2 times pi over 2 is just pi. Tan of pi is 0, so both go to 0. So therefore, we can apply Hospital's rule, and we can say that the limit as x tends to this number here of f of x over g of x is the same as the limit as x tends to the same number of f dashed of x over g dashed of x. So find f dashed over g dashed, which is this and this. So here e to the function of x differentiated is f dashed e to the function. This differentiated is cos. This of course differentiates to plus sine because this negative in front here. This goes away. Tan differentiates to x squared, you just put this 2 in front, and we just shove those things into there, and we put, you can just assess this by putting x as pi over 2 into here, and you'll get the marks for writing that down, which therefore equals this, because cos of pi over 2 is 0, so that goes away. Sine of 3 pi over 2 is, I believe, minus 1, so this is a minus 3 up here, and sec squared of yeah, I should have put some more brackets around here, shouldn't I? Sec squared of pi is is positive 1. Is it? It's minus 1, isn't it? But then you square it so it gets positive 1 times 2 is just 2, and we get this here. Good. Okay, a calculator would just tell you that. I don't know why I talked about it so much. Anyway, Simpson's rule is just a fancy version of trapezium's rule. It's actually quite interesting, but essentially you don't do an interesting thing. It estimates this integral here between 1 and minus 1. This is the function that they've chosen to put here. It wants us to do 6 intervals, does it? Yeah, it wants us to do 6 intervals. So draw a table and put 7 spaces here. So 1, 2, 3, 4, 5, 6, 7. Start at minus 1, end at 1, because there's 2 starting bits. You could start here and times it by 2 at the end, but I just chose to do it like this. And then find whatever even interval will get you from minus 1 to 1 across these boxes, and it gets you this in the end. Will work, I think, quite well. And then we just plug all of these numbers into this function here. To get whatever our y would be. So if you put minus 1 into here, minus 1 squared is 1, cos of pi over 2 is 0, so that first bit is 0, which is good because we can clearly see that should be correct. Anyway, then you plug in the rest of them and you get all these numbers. If you do that, of course it's symmetrical, so you get all these back again. And then Simpson's rule, like I said, it's actually quite interesting. It's a bit like trapezium rule, except it doesn't estimate with straight lines in between, it estimates with quadratics using the midpoint and making a quadratic there. You don't need to know any of that, because all you really need to do is have this in your head. This is all that I have in my head. The area of this, so this essentially, is roughly a third times the interval length, which in our case is a third as well. And then you do the 2 inputs, which in our case is 0 plus 0. And then what I mean by odds and evens is this is an odd, because this is the first one, right? These are the endpoints. Don't count those. This is the first, this is the third, and this is the fifth. Put those values in here. So these odds are going to be this plus this plus this. The evens, this is the second one, this is the fourth one. So put those in there and add them together. And you just literally type that into a calculator, and you get this. Now this question is about volume, so all we have to do here, we've got this area at the front face of the door, if you want, and we just times that by the thickness to find the volume. Of course that's 8.5 centimeters squared, which is 0.085 meters. Sorry, not squared, just centimeters, which is this many meters. I've changed that because this is all in meters, this original stuff here. And then we just do this times this, and we'll find the volume is that in meters cubed. I guess I could have written, but I couldn't be bothered. Okay, question number 3, vectors question here. So a to b firstly, a to b, we need to take away 2 from the i's, add 6 to the j's, and add 4 to the k's, and I always write vectors like this, just because I do. A to c, the same kind of idea, we need to take away 5 from the i's, add 5 to the j's, and add 2 to the k's, that would be minus 5, 5, 2. And now to cross 2 vectors together, you transpose the 2 vectors, put them in a 3 by 3 determinant matrix, a matrix, and find the determinant of that matrix. Put I, j, k on the top. So the determinant of this is going to be I times 6 times 2 minus 4 times 5 is going to be the first bit. So that's going to be 12 minus 20. And then minus, remember, you do minus this one j times this is minus 4, minus this times this, that's minus 20. And then plus k times this minus 10, minus 30. And we get this in the end, and that will be this. I'll put it in column form up here. find an equation for pi in the form this. Now the whole point of the cross product, well, there's two reasons you do a cross product. And the first reason is you find a normal vector to both of these things. Now if all of these three positions are in the plane, if you find a normal vector to each vector that takes you from one position to the other, that means it's normal to the plane itself. You found a vector that's perpendicular to both, to these two vectors that sort of span the plane, if you like. So this can serve as our n in here, is all I'm saying here, because it's normal to the plane, because that's what the cross product does. So this can serve as our n. We do r dot n equals p, but of course we need to find p, and to do that we just put in whichever one of these we want to. I thought this one looks the easiest, and we find p is 28, and then we have this here, and that will be an acceptable answer. You could, of course, take a factor out of this normal and get different answers, but this is acceptable. Find the volume of tetrahedron ABCD if D is this. So we have a plane with 3 points in it, we know of, and D is outside of the plane. So imagine this is 3D and D is kind of coming out of the screen here, up here, above the other ones. And we're looking for the volume of this tetrahedron here with a triangular bottom and up to D. So there's a standard way to do this with a formula, which is the volume is a sixth a to d dot producted with the cross product we found earlier. Now, of course, we already have that, so we can just put that in there. A to d is, how do you get from a to d, where you do 5 more in the i's, 9 more in the j's, 4 more in the k's, so that's going to be that. You can put that in there, put this result in there, dot those together, have a sixth out here. And just in case this is a negative answer, these just mean we take the positive of it and we get the answer here. Now if you didn't remember this formula, there is an intelligent way you can do it otherwise, and I just wanted to show you this just because it's kind of interesting. I talked about how the cross product finds normal vectors to the two vectors you use. What it also does, though, is if you take the determinant, or the magnitude, I should really say, the magnitude of the cross product result, you get the area of the parallelogram that's formed out of the two vectors you've used. So if I draw a parallelogram here, the cross product, the magnitude of this cross product here from AC to AB is the area of this parallelogram here. So if you just find the magnitude of this by doing this, so yeah, and then halve it, because I've only got the triangle on the bottom here, I'll get 6 root 5, and that's the area of this triangle here, right? So I can put that in there, and then what I can do is I can say, okay, well, volume of tetrahedron is a third times base, which I know, times height. So if I just knew the perpendicular height from D to the plane, I would be good. But of course, I've written out the planes formula in Cartesian form here. This is just all good practice for all the vector stuff you have to do in Core Pure. The formula book just gives you this formula here, which says the perpendicular distance from any point, so I'll use this point here, to the plane, written in this form, is this. So use all of these numbers. These are the n's here, and alpha, beta, gamma are these numbers here. Just put them all in, and you get the distance is this. And you can then use this formula a third, times this, times that, and you'll get the same answer as we did before. 52 over 3, I believe, is the same as what we did before. I think I got 104 over 6 before, didn't I? Just because I didn't simplify it, but the answers are the same. Good, yeah. So it is the same. Excellent. So question number 4. So a couple of different ways of doing that. Just good to know. Question number 4, using Leibniz theorem now. So x minus pi to the power 8. So we're looking to get to the 8th one in Taylor's series here. I should have put a picture of Taylor Swift up here because I was planning to, but then forgot. So let's just imagine there's a picture of Taylor Swift here, just because it's her series, and that's important. Anyway, so we're going to use r as 8 here. So you put an 8 in there, an 8 in there, an 8 in there, and we've also got k as pi. But what that really means is we need to differentiate f 8 times, right? We need f to the differentiate 8 times because we need r is 8 there. Now, of course, you don't really want to differentiate this 8 times because it becomes a bit of a mess. So that's where Leibniz's formula comes in. What you do is you separate these two functions out into one function which we'll call x squared, x to the 4, which can be g of x, and another function sine 2x can be h of x, and you differentiate all of these 8 times. So this one differentiated once is this, then this, then this, then this, and then after this, all of your subsequent differentiations are all 0, of course, right? So that's good. And then we do this one. Now this one is less friendly because it doesn't all just go away, but you eventually get it done. You can get all 8 of them done. It's not that fun, but you do it. And okay, so that means that the Leibniz's theorem says that the 8th derivative of the original function it's a bit like a binomial, isn't it? You take the original g of x and times it by the 8th derivative of h, and then you add 8, choose 1, so this is the same as in the binomial expansion, and then you take the first derivative of g and the second last derivative of h, and then you take 8, choose 2, and the next derivative of g, and then the derivative of h before that, and then you keep going until you get to the 8th derivative of g and the very first h, and that's this thing here. So that's the result that you want to use. So we plug in some numbers now. Of course, when you get to g5, everything goes to 0, and these are all products, so none of these last terms matter. I just need to get the first 1, 2, 3, 4, 5 terms, I think, is all I need to use. All right, I just need to go up to g4. So I think that's what this looks like. So just to explain this first term, g of x is this, x to the power 4. 8 of x is this, so just times those two things together, we get that. 8 choose 1 is clearly 8, times that by 4 is 32, and then 8h to the 7, or differentiate 7 times is that. And then here I just got all the 3 terms separate. So 8 choose 2 is this, g2 is this, and then h6 is that. And then likewise for the next 2 and the next 2. And then you can type all this into a calculation and get this, and that's my 8th derivative. So that's cool, we have that now. And now, of course, we can say, well, okay, we need to evaluate that at pi, right? Because we're doing x minus pi, so k is pi. So we need to evaluate the 8th derivative at pi. So we put pi in here, but of course this is quite nice because sine of 2 pi is 0. So the sines all go away, and we're just left with the 2 cos terms. Cos of 2 pi is 1. So we just end up getting rid of those as well, but keeping the coefficients. This becomes a pi cubed, and this just becomes a pi. And we have this. And now our term is going to look like this. I've just swapped x minus k to the r down and put f to the rk up here, because this ends up being the coefficient of this thing. So now I'm interested in this thing. Type 8 factorial in a calculator, you get this. Now these things don't divide to become integers, but then you notice there's a 315 here. So just do this divided by 315 to find what thing it actually is that makes it. So it's just going to be 128. You can just do that in the calculator to find this, and then divide each of these by 128, and you get this result here. And we have our 2 answers that we were requiring, and we have the answer. Good, 8 marks done. I think we're halfway through the paper here. This question is really interesting because I think you wouldn't have to know anything at all about ellipses to get 7 marks on this question, is my theory. Firstly, because okay, it seems like this first bit, well, how are you going to find the foci if you've never seen ellipses before? Well, just look in the formula book. Here it is. Everything you need to know about ellipses right here. So standard form is this. They've given us that, so we know that a is 6 because 6 squared is 36, and b is 4. So we'll use that. And then look, it says the foci are found at plus minus AE, 0. But what's E, you wonder? Well, then we just look at this and we see, oh, well, actually, if I have A and B, I think I can solve for E. So that's cool. Just put B in there with A there. Let's solve this for E. We get that E is root 20 is 2 root 5, I think. So we get this. That's pretty cool. And we'll just say, we'll simplify that to that. And now we can just put that into there with A being 6, and we get plus minus 6 times this, 0, and of course 6 divided by 3 is 2, so we end up with this, and there's going to be our 3 marks, just because we saw the formula book existed. Good. Question B then. So we make, for any point P on the ellipse, let's just draw the ellipse to get a good idea of what we're talking about. We have the 2 foci at plus 2 root 5 and minus 2 root 5, 0. And we have any point on the ellipse up here. Now, this is what this is, essentially. Parametric form is just telling you how to find a point on the ellipse. So I can say here, at this point here, I can just describe by saying it's 6 cos theta, 4 sine theta. It's just what I can say. And we're going to make a triangle out of the 2 foci and this point here. So we make a triangle, and we're thinking about its perimeter. Now, its perimeter is clearly the 3 sides added up. This length is clearly 4 root 5. Which is cool. What about these 2 lengths? Well, I think all we really need to do is some Pythagoras. If we just say this distance here, the horizontal change is just going to be this minus this, and the height is just this, of course. So if we just square those and add them up and do a square root, that's going to be this length here, I think. Of course, we square this out, we get this. Just be careful when you square this out. This you can write as 16 cos squared plus 20 cos squared. And the reason I'm doing that is because when you have 16 of them, you can factorize out that 16 with the last 2, and these just make 1, which you can then add to this to make this. And you might sit here and wonder what to do, but actually you've been given a massive hint if you look 2 lines above. Look at this thing here, which squared out to this thing here. Those 3 numbers are very similar to those 3 numbers. In fact, they're the same numbers, just the other way around. So if I just swap these 2 around, I think this should perfectly factorize into this here. right? Because the 36 just went onto this one instead, and the 20 went over there. I think that means it factorizes to this. Of course, the root and the square cancel here. Technically, I need a modulus here. Squares and square roots don't cancel properly. You need a modulus here. But it's not going to matter, as you're going to find out. So this is this length here, which I'll put there. Just move the picture to the left here, so that I can do this length now is exactly the same thing. The change in height is this thing squared, and then you've got this, I think I just ended up adding this, because essentially this minus this, but this is already minus, so it's a plus. Exactly the same thing. I just copy-pasted everything here. Do exactly the same system. You get this, it factorizes to this, they cancel out. Technically you need a modulus, but I don't care. And then you just add together the lengths, and this, of course, cancel. This is why the modulus didn't matter. 6 plus 6 is 12 plus this, and you get the answer here, which is good. Okay, question number 6. This is quite a nice question as well. We've got this seems very confusing. Like, you might have never seen like this dA, dB, whatever. Just simplify it. Just don't make it overcomplicated. All this is you've got a function in terms of t with its modded, and likewise another one. And all you're being asked for is, when is this one bigger than this one? Like, when is A further away than B? But this is saying how far away it is. So we're just looking for this to be bigger than this. That's all we're really looking for. And now that we've kind of simplified it to those terms and ignored all this fluff, we can just get out a picture and we can say, okay, well, what does this look like? Well, a line 5t minus 31 looks like this, but it's the mod of that. So as soon as it goes into negatives, it just turns around and goes positive again. So that looks a bit like this. I'm just saying t is on the x-axis, of course, because, yeah. And I've called this d. I could have called it anything I wanted, really, but yeah, sure, this. And then this here, this is a quadratic. Now, if this actually just straight up factorizes, I believe. I found, by the way, these 2 points here. I guess that's useful. This factorizes this, so this has a quadratic with roots at a third, maybe roughly here, and now 8 is slightly bigger than this, so roughly here. So it's a quadratic that looks a bit like this, but of course it's modded as well, so as soon as it goes into negatives, it immediately turns and goes up again. Now this is very hard to draw in PowerPoint, so I decided to just GeoGebra it, and this is my picture here. Hopefully you can see how this sketch, if I flip this over and made it there, would turn into this one here. Hopefully you can see that. And now what we're asking is, this is the blue one. This is the line, right? The blue one that's like this, the V shape. When is that higher up on the graph than this? That's essentially what I'm asking. Well, it's clearly higher up over here between these two, and it's also higher up just slightly for a short time in between those two, is what my sketch says. Ignore all the numbers and stuff, because obviously we couldn't sketch it this accurately. But the other thing we want to say is that t is time. Time is on the x-axis. Time can't be negative, so we're going to ignore this section of the graph down here. So time can't be negative. Going to ignore that over there, and we'll find, our objective will be to find these 3 points, right? But on this interval here, we'll just say it will be between 0. The blue graph is higher between 0 and this point. We don't need to know anything about over here because time can't be negative. So, okay, how do we find these 3 points? Well, the easiest way is just to ignore the mods, essentially, and just look at the graph and say, okay, well, what is the equation of this line here? Well, what mod functions do is, if the graph is ever negative, it just times that whole thing by -1 to make it positive. So this line here is just the line with equation minus brackets 5t minus 31. That's the equation of this line. And likewise, this red curve, that's been flipped over. It should be down here. Like this equation inside the mod should be down here. It's just been flipped over. So this red curve has equation minus all of this. In brackets, of course, because you need to negative every single thing. Then we just take out the minuses, and this, of course, this is just something we can easily solve. Divide by 3. This actually, you can just put it into calculator, you get this. And so, okay, what do we think this solution here is then between these 2 meeting points? Because, of course, this algebra here doesn't discount the fact that this curve continues, and then this line continues, and you have another solution down here. Well, this solution is clearly the smaller one, right? It's going to be 5 minus 2 root 3. And we can verify that. Yeah, it's a bit above 0, isn't it? Root 3 is like 1.7 times 2 is 3 points or something. This is a bit above 0, so good. Yeah, that should be that one. And then we look at this intersection here maybe, and we could say, okay, well, this is the intersection between the line 5x minus 31, because nothing, or 5t minus 31, because nothing's changing about this line, it's just the normal line. And this is still the upside down version of this quadratic, so it's going to be this one without the minus in front, and then still this one. And this should find us this intersection point. We'll find another intersection point as if the line continued out and met the curve down here somewhere, but we can discount that later. So we get this, we have this, and our two solutions are going to be this and this. Again, we don't care about t as -1. That's the other solution. If you were to continue this quadratic out and this line out, don't care about it. We just care about this one. So that's going to be 23/3. And then finally here, both of the curves and the line are just acting as they normally do without the mod function. They're both up here. And so we're just going to set this equal to this without any negatives at all. And we find the other solution, which is also at 5 plus 2√3. Right? And some of you may have noticed when we found this solution back here, if you think about continuing this line out and continuing this curve out, by symmetry they're going to meet at the same x coordinate as the two meet up here. And of course the algebra confirms that, because of course if you put two minuses in front of this, that's the same as putting no minuses in front of either of them. So of course these are going to have the same answers, and we have that this is 5 plus 2√3. So you could have got that without doing any of this if you had been aware enough to notice that. So well done if you were. Anyway, to finish this, we just need to say that the blue graph is above the red graph between 0 and this, and between this and this. And I think that will be my answer. Was t allowed to be 0? I'm not sure whether I was okay writing this. Who knows? I'll check the mark scheme later. I can't be bothered to think about it right now. Yeah, sure. Anyway, it's recorded that the distance to the particle from B was less than from A for approximately 4 seconds. So essentially it's saying that this result should be about 4 seconds if the model is good. So what we do is we just add up these intervals. So we say, okay, well this interval is clearly 5 minus 2√3 long, and this interval is this minus this long. So we add up those 2 times, and we get this answer, and that's a long way from 4, so this model isn't good. So 1 mark for finding the time predicted by the model, the sum of the intervals. 1 mark for that, and then 1 mark for saying that's probably not very good, is it? Because it's quite a long way from 4. Excellent. Just a couple of questions to go then. One about a parabola. So this curve here looks a bit like, I don't think we're not given any marks for drawing it, but you should do anyway. Curves of the form this look like this. It's just a quadratic on its side like this. So that's cool. It looks a bit like I've drawn that a bit too low, but we'll ignore that issue for now. That should go through. That should totally go through the x-axis. We'll pretend that I drew that accurately, but it should be perfectly symmetrical around the x-axis, of course. I think it's close enough to be considered okay. Of course, like I just said, there are no marks for this, so I'm not going to be criticized too hard for that. You've got a point here and a point here. I'm just going to put them there and there just to make this whole thing easy for me to draw. And we've got an equation of the line that passes through P and Q. So we've got a line that goes through like this. Find the equation. Well, okay, the rise is going to be 18p minus 18q. And the run is going to be 9p squared minus 9q squared. So that's cool. And then we just say, well, we can use y minus y1 equals mx minus x1, I guess. If we just choose this point, so y1 is 18p, x1 is 9p squared. M is, of course, this divided by this. Now, as soon as I wrote this down, I realized it's a difference of 2 squares, which is good. You can divide all of this by 9 to make this. And also, once you did that, p squared minus q squared is p minus q into p plus q. And, of course, this becomes 2p minus q, which is 2 brackets p minus q. Cancel those out. We get this. And then I think what I did was just notice, okay, well, they want a p plus q times y. So let's times everything by p plus q to make this. Which seems helpful. And now I'm going to expand this out, but I'm not really going to. I'm just going to do y times this is just y times this minus 18p times this. And then I've also expanded this out. And now what I notice is this makes a minus 18p squared, which will cancel with this one. And then I also have a minus 18pq, which I can then move to the other side and factorize out the 2, and I end up with it exactly like they wanted me to get. So that's good. Probably an easier way of getting there, because it seemed like I did quite a lot of algebra there, but that's okay. Next picture looks slightly different. We have a normal to the curve at P, so that's this one here, and a normal to the curve at Q, which looks like this here. And they're talking about the meeting point of A and telling me the coordinates look like this, and they're asking me to show that. So okay, what we do is we differentiate this curve, because normals are of course about gradients, so let's do some differentiation. This differentiates as 2y dy by dx, just some implicit differentiation there. 36x divided by 36, divide by 2y, and then cancel the 2's. And then, of course, therefore, the gradient at this point here of the curve, just put in the y coordinate to find that the gradient of the curve here is 18 over 18p, which is just 1 over p. So the gradient of this curve here is 1 over p, so therefore the gradient of normal is minus p, because minus p times 1 over p is minus 1. Exactly the same thing here. No marks for getting that this is just going to be minus q. It's just all the same thing, just with q's. So that's the gradient of this one. And then we just need to find the equation of each of these. And we can do that by again doing y minus y1 equals mx minus x1 for each of these. So this first one is referring to this line here. Y minus y1 equals m into x minus x1. And then we do the same thing for this one, and we get a very similar equation. And if we solve these two things, we should find the intersection. So okay, that's if we add 18p and add 18q to both sides, we'll just get y equals both, and then we can just set them equal. So I think that's what this is here. So add 18p to both sides, and then just set them equal to each other because they both equal y, and we get this, and solve this for x. Now be a bit careful because you're trying to get this thing here. So what we do is I expanded out. There's probably other ways to do this, but I just expanded them out. I then put the x's on one side to give me this, and everything else on the other side. And now you probably can't factorize this without a bit of time on your own, but just look at the answer, right? Just look at the answer. This is claiming that if I divide both sides by q minus p, hopefully, as long as I haven't made a mistake, I'll get this. Now there's 9 into brackets here, so let's just do that first. And now just blag this, right? Just be confident enough to write this, right? Just pray, just write this down. I haven't factorized this, I'm not a genius. I've just written down the thing that's in here and just hoped that if I put a q minus p out here, which will cancel with this one here because q isn't equal to p, I'll just get the answer. And of course, expanding is so much easier than factorizing. You can just verify by hand that this does indeed expand to this, and so I'm good. I've got this okay, I think. I've done all right. So these now cancel, and we just end up with the answer here, which will be this there. So that's our x-coordinate, and of course all we have to do to find the y-coordinate is take one of these lines here and just put the x-coordinate into it. So I just chose this one apparently. It doesn't matter which you do. Expand the 9 out first to get this, and also I expanded out the q for the whole thing, I think. Lots of things cancelled. I like using these cancel lines, so I did it. Y equals this, take out the minus 9. Both these have a PQ in them, so take that out as well, and you end up with this here, which is this one here, and we have that answer as well. Good, so the last part of the question now combines both pieces of knowledge. It tells us that, yeah, sure, we have these two normals meeting at this point that we said. We also have this line, which is of this equation. We're told now that the line goes through 12, 0. And it tells us to find, in the form this, an equation for all the places where A can be, under the single limitation that this line here goes through 12, 0. So okay, what we say is if this line goes through 12, 0, that means that when x is 12, y is 0. So we put that information in and we find this here. This is all 0, this is 24, move it over, and this is this. I'm going to halve this and you'll see why. Next, what we can say is, okay, looking back at, what am I looking at here? Looking back at this thing here, this is the point A, isn't it? This is the coordinates of the point A. But if I know PQ, or 9PQ is minus 12, expand out the 9 here, and we end up with a 9PQ there, which I can replace with minus 12, and then I also have a plus 18, so that makes plus 6 in there. And likewise, this minus 9PQ here is equal to, should be equal to plus 12, should it not? 9PQ, that should be a plus 12, should it not? Because 9PQ equals minus 12. And then times by that should be a plus 12. I've just remembered why that doesn't make a difference, but I've made a mistake. That should be plus 12. You'll see why that doesn't matter. So what this means then, if you imagine this as a plus 12, is that the x-coordinate is this, and the y-coordinate is this. That should be a plus. Now what I'm going to do is I'm going to square the y-coordinate. And that's why this I didn't notice that this was a mistake, because when you square it out, it goes away anyway. But square this for that, and then square this for that. This is, of course, p plus q times p plus q, which is this. And now 2pq, if I try and get a 18pq in here, that means taking the 9 that's in here and multiplying it out, leaving behind a 16. 9 times 16 is this. Put the 9 into here. 18pq is minus 24. Replace that with there. And now, hopefully you can maybe see what I'm going to do here. This is looking quite similar to this over here. So if I take away 30 from this here, we end up with this, which is almost close to matching. And if I times this by 16, we get this, and they now match, which means y squared equals 16 into x minus 30. So that's the answer here. It is correct. I didn't notice this plus It should have been a plus here, and I just didn't notice because I squared it out anyway, so it didn't matter. But yeah, this will be the answer. I think I probably would have lost a working mark for that, I presume. But who knows? Yeah, sure, who knows? Anyway, question number 8. This is just a great question. This thing at the end in particular is really tricky. But I mean, it's the last question in FP1, so maybe it should be tricky. We start with a T-substitution. Now, you're not given anything about T-substitutions in the formula book. So, okay, tan of x over 2, so we get out a triangle x over 2. Tan of x over 2 is opposite over adjacent. That's t over 1, which is t. So this thing here refers to this triangle. Tan of this is opposite over adjacent. T over 1 is t. But of course, this means that this length is 1 squared plus t squared square rooted, which is this, which means sine of x over 2 is this over this, and cos of x over 2 is this over this. Now, you don't need to do any of this. If you remember your T-substitution formula, you don't need to do any of this, but I'm just showing where you would get it from if you ever forgot, or if you wanted to make sure. If you wanted to make sure you had lots of time, if you're the kind of person who has lots of time in the exam, just do this, because now what we can say is, well, okay, using this formula, which kind of is in the book, as long as you set a equal to b, you'll get this pretty easily, and then replace theta with theta over 2, and then just put these two results into here, and you can find that sine of x, you're replacing theta with x, I guess, is this. This multiplies out just to make this here. And that's a result that you can just write down. You're just allowed to write it down. You can just remember it. And you can do some similar stuff with some similar trig to find cos of x is this. And then once you did that, you could do this divided by this to find that tan of x is this over this, because these two bits cancel, and tan of x is that. So if you're using a T-substitution, either know how to derive the results by doing this. I haven't really derived this one here, but I'll leave that to you. Or you just remember these three things here. Right? Those are your two options. So I'll just write, I'll continue with this, then I'll just leave these three up here, and we'll lose all of this stuff. Anyway, show that f of x can be written in this form. So now we replace sine of x with this, and cos of x with that. We get this. Times top and bottom by 1 plus t squared, I believe, is probably the best idea here, partly because you can see the result that you want to get here. I've expanded out this 5 into here, and this 6 into this here. And this ends up being this. Now, you can quickly verify that this does equal this, but what's the easiest way to show it? Well, I thought the easiest way to show it was probably to factorize out the 2, because that's what they want me to do here, and also deliberately leave a plus 6 alone. So I can write this as plus 2 plus 6, and then when I factorize out the 2, I get a plus 1, and then plus 6, and this, of course, factorizes straight into that, and we get exactly what they want us to show. Good, so now, yeah, I'm just going to leave these results here, and we're going to move on to the next bit, hence solve this thing here. Now, we've just said that f of x can be written like this, so we're just going to put this straight instead into that. And just remember that if we do this, we're going to solve for t, of course, so we're then going to have to use this at the end with our t answers to find our x answers. That's all we're going to have to do at the end. So yeah, we have this, let's solve it. We can just cancel out these 3's immediately. Times by 7, times this across, we get this. And then, of course, we can just solve this. We get t is, this actually factorizes, not too hard to notice, is going to be this. And so now, yeah, we use this here, so we have either minus 1 over 11 is equal to this, or we have minus 1 is equal to this. Either way, of course, if you're solving for x over 2, you're only going to have to look between 0 and pi, according to this range. So do tan inverse of this, we get that, but of course that's negative, so not really very interested in it because of the range here. So we get out the tan graph and we say, okay, well, minus 11th, a line along here somewhere. We found this solution up here, not interested. Let's do pi minus that solution there, and we'll get this. And that is the thing that we're interested in, times by 2, and we get this, and that will be our first solution. And then, of course, we set minus 1 equal to tan of x over 2. Do the same thing. Tan inverse of that you might want to recognize as just minus pi over 4. It's just this one here, minus pi over 4. Do pi minus that to find 3 pi over 4. 3 pi over 4. And then, of course, times that by 2 to get 6 pi over 4, or 3 pi over 2. And I wrote that as a decimal just because it said so. That's that one as a decimal, and that's that one. Good, and those are our two answers. This last bit is absolutely incredible. I was so proud of myself for doing this all. Yeah, just really, really nice. The answer, when they give you stuff like this, you've got to use the answer. You've got to be on top of it, and think that I think this question would be harder to get right if they just said do this. Like, this is really helpful here. So anyway, we know f of x can be written like this. So we can put that into there. I've got rid of the limits because, of course, I put t into here instead of x. So I have to change the limits. So I'll do that. And I also have to change this dx, of course, right? So let's look up here. dt by dx is just this derived, which is just going to be tan derived to sec squared. We saw that way back in question 1. Just bring the half out. And then, of course, times, I wrote this as 1 over 2 cos squared, just because, yeah. And that, of course, made it easier for me to see. Just times by dx, just times by this, and we get this, and we can replace that instead of this dx, we can write all of this stuff. Now, of course, that's not great, because I've written an x in here when I'm trying to integrate now with respect to t, so we need to replace this with some t's as well. And this is actually where, going all the way back, me actually deriving some of these results actually comes in handy now, because earlier we saw this result. Just thinking about the triangle that's formed when you drew that, if you want to go back to it, you can do, but I did write this down earlier. So of course, just square both of the top and bottom here to get this, and then just replace that with a 2 to get 2 over this, and that can just go straight into there. There should be a 2 in here somewhere. Where did that 2 go? Oh, I cancelled the 2 down here. So I think this all makes sense, yeah. I cancelled the 2 and made that a 3, so I cancelled it out. Cool, that's fine. And now, of course, this cancels with this, and we end up with this, and that's looking good. I still need to change the limits. That's the last thing for me to do here. So, okay, we say when x is 4 pi over 3, this becomes 4 pi over 6, which is this. So this top limit becomes a minus root 3. When x is pi over 3, this becomes pi over 6. T is this, and so the bottom limit becomes 1 over root 3. Now be super, super careful here, because you're risking losing some marks if you just do this. And the hint is in here. There are 2 arctans. And we'll get out the formula book in a second to look for what the arctan integral looks like. But the fact, this should only really become one of them. So why are there 2 of them here? And I think that was the big red flag that enabled you to spot this. But the tan graph is not continuous between these 2 points here. Between pi over 6 and 4 pi over 6, which is on the other side of pi over 2, we have this discontinuity. So what we need to do, if we're integrating between here and here, is we actually need to break the integral up between there and pi over 2 and, well, pi, because this graph technically isn't correct. So here and up to pi over 2, let's just pretend, and then pi over 2 up to here. Now, why have I written pi here? Well, because the transformation is x over 2. So we've actually transformed this graph out. We've shifted it out factor 2. So the asymptote is actually at pi, which is why I've made that at pi instead. So, okay. So we need to split this up into here, and then we also need to say, well, what happens when you put pi into there? Well, of course, tan of pi over 2 is infinity, so we end up with this thing here. And then what we do is we say, okay, what we can say is this integral needs splitting up, and we'll replace all of these, just like I have here, and we'll replace all of these inputs with these 4 answers here. So we'll go from 1 over root 3 here to positive infinity, and then come back from positive infinity down from negative infinity, and then finally up to negative root 3. And that will be our integral here. And that will be what we do. And then we get out the formula book and we notice, okay, well, this is great because this will give us 2 arctan results. Something happened to the... except it's not quite in the right form, is it? Because x, I completely forgot about this, x is 3t plus 1. Right? This x squared should be a 3t plus 1, but that's fine because we can just use a substitution, a second substitution. U is 3t plus 1, so of course du equals 3 dt, which means dt is 1/3 du. So replace these with u's and replace these with 1/3 du's, and also change the limits. Now, when you put t into here, 3 times infinity plus 1 is still infinity, minus infinity is still minus infinity. 1 over root 3 times 3 is root 3 plus 1 becomes this, and then minus root 3 is minus 3 root 3 plus 1 is just there. So we've changed all that, we've put the u's in, we've replaced these with 1/3 du's. The 3's now will cancel, and we're finally ready to use this formula exactly right, with a being root 3. I think as long as a is root 3, this is exactly right, so we get this. I've also just, and then the 1 over root 3 at the front here as well, of course, which doesn't need to go inside of these bits here because, of course, we're not substituting anything into there, so I can just leave it outside. And I think we have this. I think at some point I start remembering that I'm supposed to write arctan, I think it's here. Good, yeah. So we put in infinity. Our arctan of infinity is just pi over 2. We can sort of pretend to say, and then we put in this here, and we get this, so it's this minus this. Tan inverse is the same as arctan. I've also, and then I've done it here as well, and then arctan of minus infinity is minus root 2, pi over 2, so we get this. This becomes a plus root pi over 2. I'll factorize out the 1 over root 3 to make all this, so it's pi minus this plus that. Pi over 2 plus pi over 2 is pi, which is amazing. This is looking pretty accurate. Just these bits that are wrong now, so rationalize these, times this by root 3 over root 3, which of course give me a 3 on the bottom. This times root 3 is going to be, well, this times root 3 is 3, so it's going to be 3 times 3 is 9, so minus 9 plus root 3, which I think is pretty much exactly that. And then this times by root 3 over root 3, this becomes a 3, that becomes a 3, that becomes a root 3, we get this. Both of those are the wrong around, so I'll just write it down exactly the way they want me to here. And I think we have the right answer. And that was an incredible question to finish. I hope that I didn't do it too badly. But yeah, really impressive if you managed to get that trick with the, we should say k is 1 over root 3, shouldn't we?